So in this video we will be continuing with our introduction to design of water tanks. So here we are going to discuss regarding joints. The IS 3370 Part 1 2009 Clause 10 gives the detail regarding joints, the various type of joints that we are using in our water tank. So the first one is movement joint. Movement joints. Second one is construction joint, and third one is temporary open joints. The movement joints again can be classified as contraction joints, expansion joints, or sliding joints. The contraction joints can be either complete contraction joints or partial contraction joints. So these are the figures. The first one is the complete contraction joint. What is complete contraction joint? This joint is a flexible joint. Here the left and the right portion is discontinued. Both the concrete as well as the steel are discontinued. But here there is no initial gap. There is no gap between the left and right portion. But there is a discontinuity. And in order to prevent seepage of water through this gap, through this discontinuity that we have generated, we are using joint sealing compounds and water bars. This can be also called as water stops, which is a flexible tape-like element or material in order to prevent seepage of water. In case of walls, it is provided at the midpoint, and in case of slabs, floor slabs, we are providing at the soffit of the slab. And in order to take the shear stress, we can give a shear element also. Or a shear key. The second type is a partial contraction joint. The name itself indicates it is partial. What is partial? What is partial here? It is the continuity in steel reinforcement. Here, the left and right portion, there is a discontinuity in concrete, but the steel reinforcement is continuous. And in order to prevent seepage, we are providing joint seal compound and also strip painting here. This is without any shear. In case of expansion joint, the difference here is we are providing an initial gap. There is a gap between the left and right portion. Here also there is a complete discontinuity in concrete as well as steel. And in order to prevent the seepage of water through the joint, we are providing joint seal compound or strip painting, etc. Also, we are providing a water bar in between, as we have discussed earlier. The gap in between, this initial gap, is filled by some filler materials that is being shown over here. The fourth type is the sliding joint, or the third case of a movement. The third classification in movement joint is a sliding joint. This is which is shown over here. This sliding joint is normally provided in between the wall and floor. Here you can provide a joint sealing compound. You can see a strip painting, and also the prepared surface, sliding surface, or a rubber pad is used for the flexible joint. The second type of joint is the construction joint. So where it is used? This construction joint is introduced as for the convenience in construction. Suppose we are not in a position to complete the entire work in a single stretch, we need to use this construction joint. There, the top or bottom, in case of a wall, or a left and right portion in case of slab. These are discontinued, but the surface is prepared such that there is a perfect continuity between the sections. Also in the design we are assuming that there is perfect continuity, so we have to make sure that in practice also there is perfect continuity between the sections. The third type of joint is the temporary open joints. The temporary open joints you can see in all these bridge construction. This can be complete or partial, as in case of the contraction joint. Here the difference of this particular temporary open joint compared to our contraction joint is that we are having an initial gap which is later filled with concrete. This is the only difference with this when compared to contraction joint. The second topic that we are going to discuss in this video is the behavior of circular tank with rigid joint between floor and wall. This we have discussed in the previous video also, but we will be discussing more in detail here. So here the wall and the slab is made monolithic, or it is fixed at the junction B. Okay, so the deflected shape of this tank wall is shown by ACB. The upper part of this tank will be subjected to hoop tension and the lower part will be subjected to cantilever bending. For shallow tanks of large diameter, this cantilever, as in this figure, the cantilever action will be more predominant. And in the case of deep tank with small diameter, as in this figure, deep tank with small diameter, the hoop action will be predominant. This is the hoop load distribution as well as the hydrostatic distribution. We will be having the hoop action as well as the cantilever action. This figure shows the bending moment diagram. At the base you are having the maximum moment, which is negative, or you can have a tension at the inner side, and you can the moment positive moment M in between at the near about the midpoint. You are having a positive moment also. Okay, so this is the bending moment diagram of such a type of tank. So the analysis of these fixed tanks are quite difficult. And these are some of the methods by which we can analyze these tanks. The first one is Reisner's method, and second is Carpenter's simplified method, and third is Approximate method, and fourth is I/S method. So we will be discussing about Approximate method in detail in this particular video, and we will be solving one problem using I/S method in a different video. Okay, so in this video, the next topic that we are going to discuss is the Approximate method of analysis. This method can be adopted when design tables are not available. For example, if you are not having the Reisner's table, or if you are not having the simplified Carpenter's table, or if you are not having the design table as per IS 3370 part 4, then we can go for this approximate technique. Okay, here it is assumed that for h squared by dt value, if it is varying between 6 and 12, the cantilever action will take place for a height h is equal to h by 3 or 1 meter, whichever is greater from the base. Okay, so in case of h squared by dt, if it is varying between 6 and 12, the cantilever action, the small h value will be h by 3, the capital H by 3 or 1 meter, whichever is maximum from the base. And when your h squared by dt value is between 12 and 30, the cantilever action will take place for a height h is equal to h by 4 or 1 meter, whichever is maximum from the base. The figure shows the hydrostatic pressure distribution A, B, C. You can see the load taken by hoop action up to the D1 portion, A, B, D1, and B, D1, C is the load taken by cantilever action. Okay, so the cantilever action is predominant till height h from the base, with the load distribution as 0 at D and WH. This WH we are getting from the load distribution diagram. WH from at BC or at C. Okay, and the hoop action is predominant with maximum at D1. That the hoop action will be WH in W into H minus H at D1 and 0 at A. Okay. The cantilever reinforcement, we are providing the cantilever reinforcement up to height h at the inner face or at the water face. We are using clause 8.1 of IS 3370 part 2 2009 for the reinforcement details. Okay, here the cantilever action is by bending, so the reinforcement will be found out by the formula m by sigma STJD, which we have discussed in the previous video. So above this height, spacing of cantilever reinforcement can be increased. Why? Because above the height h, the hoop action will be predominant. Hoop action is predominant. So at this height, cantilever action is predominant. So maximum reinforcement is coming up till this height. So suppose this is the section that we are talking about, and this cantilever action will be predominant in the bottom portion. So we are giving reinforcement like this, and then towards the upper portion, the spacing between the reinforcement can be increased. The spacing between the reinforcement can be increased, and to the bottom portion we are giving the maximum spacing. Why? Because the cantilever action is maximum at the bottom. Also, if this is the wall, then this wall is bending like this. If the load is coming towards this direction, the wall will be bending like this, and the inside portion of this portion, the inside portion will be subjected to tension, and the outside portion will be subjected to compression. That is why we are providing reinforcement at the inner face or the water face. Okay. The next reinforcement that we have to provide is the hoop reinforcement. The maximum hoop tension that we have seen is at D, and the value of that hoop tension is W into H minus H into D by 2. It is coming at D. How the reinforcement is found out? This is direct tension, and we are using the formula Ft by sigma St. This also we have seen in the previous video. The hoop reinforcement is provided in the form of rings, and again this will be subjected to the reinforcement details that we have discussed in IS 3370 part 2 from the clause 8.1. The spacing of reinforcement will be kept constant till a height h from the base, and above h the spacing may be increased in accordance with the hoop tension at that particular section. That means at this till this point we are keeping the hoop reinforcement at a constant spacing as shown in this figure, and above this we can increase the spacing of the hoop reinforcement in accordance with the hoop tension at that particular section. So if this is the section we are taking, and if it is at a distance h dash, then the hoop tension at that particular section will be W into H minus H dash into D by 2. So in accordance with that hoop tension, we can provide the reinforcement. So this much was what we are discussing in this video. Thank you. Okay.